Okay, so today we're going to talk about work and energy. That's the main thing we're going to cover. In fact, today what we're going to cover, even though, like I said, there's two separate PowerPoints, is we're going to cover work and power for today. Those are the two concepts that we'll cover. But we're actually to cover a lot more in this entire unit. Now, the unit actually is under conservation laws. And the reason why it's under conservation laws is because in physics, there's actually several conservation laws. There's conservation of mass, conservation of charge, and then there's two other laws, conservation of energy, and then there's conservation of momentum. Now, obviously, we haven't dived into some of these, but we're going to go into conservation of energy. And if you think about what conservation means, it's essentially conserving a value. For us, we're going to find that as long as there's no external forces acting on your system, that the initial energy, be really specific, the total initial energy of your system should equal the total energy final of the system. That's assuming, sorry for my writing, no external forces. In fact, we're going to talk about this in terms of work, but it's still related to forces. Close my door here. Like that. So we're going to talk about this toward the end of the unit here. This will be the last thing I'll talk about. You'll actually do a lab with this. It's a very visual unit. We're going to be using graphs to help us visualize this transfer of energy and how energy is conserved. After break, we're going to do momentum. I wish I could do them together because they really do go together, but it's just the scheduling the way it works. And what we're going to do is, after break, we're going to do a big lab where you're going to verify both conservation of energy and momentum. And you're going to get a choice of labs, so I'm going to give you a couple different choices. They're going to be fun. Some are just colliding things together. One is a ballistics pendulum where you're going to take a Nerf gun, you're going to shoot something, and you're going to find out how much energy is lost in a collision. I have a marble lab. I have lots of choices for you to do this. But ideally, we're going to group these two topics together and learn about the lab. It'll be a couple of days. It'll be a lot of fun. It's a really good thing to do. And after, like I said, after break, we'll do momentum. So we do have to start somewhere, and we're going to start with the concept of work. So these are some of the big ideas. I'm not going to read them for you. The most important one, though, is conservation laws, big idea number 5. I don't really number big ideas. This is just coming from a physics website. But the idea is that changes can occur if you change if you have an outside force. That's really what you need to know. If you have an outside force, it will change the conditions. But if you don't, your conditions will be conserved. So today we're going to talk about the concept of work. What does it mean? We'll talk about the signs of work. We'll talk about how to calculate regular work and net work. Of course, I'll define all these things. And then what we're going to do is talk a lot about transferring this energy. What does it mean? So, for example, with positive work, we're going to be gaining energy. So we're going to relate this all to energy. So first off, we're going to talk a little bit about work. What work means is how effective is your force. So on the video, you'll have to use your imagination, but for class. So imagine that I have this object right here. It's a water bottle. I'm going to put it on the table. And let's say I want it to go forward toward the classroom. I want the water bottle to go forward toward the classroom. And I can make it do that. The most effective way is to provide a force forward toward the classroom. I've now moved that object. I know it's really simple and obvious, but the way I apply a force doesn't always make the object do what I want. For example, if I wanted this object to go toward the classroom and I press straight down on the water bottle, very silly, but what happens? Nothing, right? This is not an effective force to make it move across the room. So using the context, there's no work here. The force is not doing what I want. versus there is positive work here, in this case, moving it forward. So when we talk about work, it's how effective it is to move an object. That's kind of like a very simple way to put it. So like how effective and I'll post these notes as well. So this will be a PDF to move object. And it depends on how much force, and it depends on where you want it to go. Those are two very important things. Now, I did kind of advertise that we're not going to do direction, but for this part, we do have to pay attention. So we have to pay attention to how we push something, or the direction of the force. There we go. Sometimes my pen locks up, so sorry about that. So the direction of the force. And then we have to do the direction of your distance or your displacement. And then we're going to be asking the question about energy. Now, I haven't defined energy, so I know that. But I think from your instincts, you know something's pretty much energetic through motion. Right now, my water bottle at rest is not really energetic. We don't see that it's moving in any way, versus now I'm going to push it. It has some energy. So my basic, not really defining energy definition is motion. Okay. But we're going to be asking that question. We're going to be asking, how does this change the motion? Oops, let me go back. Okay. So we can quantify how effective, because we can think about it conceptually, which I'll have you do anyway. But to quantify how effective your force is, we're going to look at the force of the object, and most importantly, the direction, and displacement or distance, and its direction. Those two actually matter as well. So we'll do some calculations later. But the calculations are actually pretty straightforward. You're going to multiply force and distance. There's nothing more to this, so that's the good news. Although I talk about it later, the units for work are called joules. Oops, I spelled that so wrong. Joules. There you go, with a capital J. That's a unit of energy and work, joules. But like I said, I'll calculate these values later. We're going to talk about it conceptually first. So we can have what are called signs of work. You can have positive work, negative work, and no work. So I'll describe those characteristics. How's everyone doing? I know people are writing. Okay? Yeah. Let me know if I go too fast. Okay. Positive work. The condition for positive work is the following. Force and distance are in the same direction. That's what it means to have positive work. Now, it doesn't have to be to the right. It could be, the force is being pushed this way and the object's moving this way. This is still positive work. What you're saying with positive work is that this is the most effective way to move the object. With positive work. And in fact, when you do positive work, again, the orientation of the arrows don't matter. I could do something like this. This is still positive work. Is that you actually change the energy of the object. And take a wild guess. If this starts at rest and this now moves, is that a gain or loss of energy? Gain, exactly. We're changing energy by gaining energy. This is a gain of energy. So another key word for this is speeding up. Notice that the water bottle was at rest and now it's moving. This is speed up. I mean, it's not going fast. I mean, it's not exciting here. But there is a change in the object's energy. Again, relating energy to motion in this case. And I know this is a video, but you can always stop me and ask questions, because even if you know, maybe the people in the video might have questions too, so just know that. So anyway. So in this case, it gives energy to the system, just answering these questions really quickly. It gives energy to the system. It doesn't take away any energy, just gives it. I guess I do this as a choice, so your 3 choices, it's this one, gives energy, the first one, like that. So that's positive work. The biggest example of positive work is just pushing an object in same direction as you intend. So, same intend, oh boy, I could spell. Intend. There we go. I also like the skier and pole example. So you ever see a skier, if anyone skis, in order to like move themselves, they have to take their ski poles and they have to push themselves forward. You're gaining energy when you're doing this. This is positive work. Or if you push something like as mediocre as a set of keys, that's positive work in those cases. So positive work, and that's supposed to be ski poles, but my pen is being finicky today, so I'll write it with the mouse. Not bad. Ski poles. Anyway, we'll let that go. Ski poles. So that's positive work. I have all this stuff that I said. There it is. Okay, negative work is when the force and the object's direction are opposite each other. So with each other is positive, against each other is negative. Hopefully that makes sense. Once again, the orientation of the arrows don't matter. So if I made this force up and the distance down, that's still negative work. So it doesn't matter. As long as they are against each other. Opposite, against. Oops, oh man. I think I'm nervous, that's why I can't spell. So against, like that. So, in this case, I'm actually going to give you an example first. The biggest case, or example, is friction. And what do we know about friction? Does friction give energy to, or does friction give speed to things or take away speed? Take away speed. So this is a case where energy is taken from our system. So in this case, this is an energy loss. And then we're slowing down, we're losing speed. So, I mean, I could use the skier example again, but just in a different context. Like a skier, like gliding to a stop. I guess gliding, I don't know, I chose that word, but you know, you're at the point where you're not using your poles and you just kind of keep going until you stop. Excuse me. So like taking this jar, and after I push it, watching it slow down. That's negative work. So we're actually revisiting motion again. We're just explaining it differently. So that's the biggest thing, is a different way to explain motion. No work. So there's actually 3 ways we can display no work, even though I have it a specific way here. The first way, so no work, and no work can also be categorized as 0 work. So these are both synonymous. There's 3 ways. The first way is the direction of the force and the distance. They are perpendicular. This is wrong. I just noticed that. Don't read that. Now, just like the example I did before, if I want to move my water bottle forward, but I push down, we can see that the object doesn't do anything. It's not a boring demo. Nothing happens. There's no work done. Or in other words, we can even describe it as no change in energy. So work is related to energy, and if you have no work, then you have no change of energy. And we can see that the water bottle is motionless. It doesn't change its energy in this case. I could also lift it, but it's not doing what I want it to do, which is going forward. That energy is going to the wrong place. So this is true. This is no work. And it does look like it has energy, so yeah, that's counteracting kind of what I said. But it has no energy going forward. That's the other idea. It's where we're putting that energy. So the other two ways you can have no work would be to make one of those two values 0. So a quick example. This is a silly example, but worth saying. If your force is 0, if I don't push this water bottle, nothing's going to happen. That's no work right there. And then the opposite's true. No movement. Now I could push something and not move it. So a quick case of that would be, like if I were to push on this board, I'm pushing on it. It doesn't look like it. I'm pushing harder on it. I don't want to push it too hard, but I am pushing it. But you can see, obviously, this thing's not moving. There's no work done here, even though I'm pushing it. And I could be exhausted from pushing it, but no work is done there. So 3 ways for no work. Also, something I want to highlight too is the constant speed. That's another way you can identify if there's work done or not. If you see the word constant speed, then work must be 0. So that's another way to think about it too. A couple different key words for the scenarios. Alright, so, if I understand it correctly, and I think I do. Oh, I'm just going to say something, don't worry about this. We have a case where there is, you have all the work here, horizontal and vertical. There is an in-between. We're not going to do the in-between, but I just want to let you know that there can be in-between. In other words, there's an angle. And what you do to rectify that is use a cosine, which selects the part of the force that goes in the direction of motion. That's all it does. We're not going to do it, but it's worth mentioning. Okay, so I'm going to pause for a second, and then what I'd like you to do on your own right now is to figure out, based on the scenario, what kind of work is present. So you'll see this on your homework. You'll also see this on your practice tests that you're going to be taking. So, also a note on the homework, there's work homework and there's power homework. They're actually 2 separate homeworks, but I'm teaching both today. So I just want to give you a heads up on that. They're both combined here. So I'm going to pause the video. I'm going to pause for a second. And I want you to try these on your own, and then we'll discuss them. That's okay. So what I'm going to do is, even though we pause for a second, I'm just going to talk about it through the video. And talk about what the answers are and what they mean. So you can check your answers and we can talk about it too. So, oops, sorry. There we go. Okay, so a teacher applies a force to the wall and becomes exhausted. Actually, what do you think? Positive work, negative work, or no work? No work, you're right. No work. And what was the key to understanding this?
The wall.
Yeah, right? The wall doesn't move. So D is 0. So good. The next one, a book falls off the table and free falls to the ground. What do you think? So positive work. That is correct. Gravity's acting down, and which way does it move? Up or down? Down. Even though the arrows are pointing down, they're the same direction. Positive work. It would be negative work if we did something like if I threw the book upward. Force up. Actually, no. I don't want to do this. Sure, we could do it that way. If I threw the book upward, so the distance would be down, but gravity would be, I said down. Distance would be up, gravity would be down. This would be negative work because they're opposite each other. So disregard their direction, look at their relative placement. So that's for that one. The waiter. Anyone know what that one is?
I said no. Because of constant speed. But technically, the waiter and the meal's going the same direction.
I was thinking just above the head. Your question I don't know how that's possible.
So depending on how you can interpret it, I can accept a different answer. The immediate answer is the keyword constant speed. And when you see the word constant speed, the work will be 0. But there's a couple other ways you could think about it. Here's the tray, and it's being held, so the tray is being held upward, but the object is moving this way. So what you have is a force that's up, but a movement that's perpendicular. So that's another reason why it's work 0. If you go into great detail and say, well, the person itself is pushing forward with their feet and they're moving forward, I would say positive work for that. But that's, you have to consider the whole person, not just the tray. So carefully, if you explained this, I would have accepted it, because that's right. But this is the correct reasoning for that. So constant speed and the direction of the force and displacement. The last one, accelerating rocket in space. Positive work. That's right. Keywords accelerating, which usually implies, movement of speeding up, right? So on your homework, you're going to have very similar examples. I'm going to ask, positive, negative, or no work. And you'll have a scenario to kind of use that. Questions on those? Okay. Moving forward. This is just an example. These are the units of work, joules, a couple other units, Newton meters, because force times distance is a Newton time meter. The bottom right here are just non-standard units of work. I just throw this in the homework just to get you familiar with them, but I'm not going to test you on the non-standard units of work. I'm just going to tell you that right away. But I'm just going to go through this pretty quickly since I'm just going to move forward. So I'm going to show you how to calculate work and then how to calculate net work. So for work, you have to know what work you're solving for, which I know sounds redundant, but if you notice on the diagram that I provide for you, you have 3 different forces. So if you were to just kind of blindly do this, you'd be like, well, which one do I want to use? Which is why you have to be specific. So which work? By gravity, by normal, or by applied? So you have to ask that question. So I'm going to demo all 3 of those to show how the calculation would change. So if I start off with A, force applied, the force applied will be work applied is equal to force applied times d. APP is just applied. I like to use arrows or direction to help me with this because it does determine your answer. So my force applied is 10 newtons to the right. Then I'm going to multiply that by the object's doing work by moving the object 1 meter to the right. Now the reason why I'm writing this a little weird and different with the arrows there, because the arrows tell me the sign, if it's positive or negative or 0. So if they go in the same direction, is that positive, negative, or 0? Positive. The answer is positive 10 joules of work. And this is from specifically the applied force. For this unit, I am going to ask you to put a plus sign next to it, because I want to really know that that means positive. I know it's a little silly, but I'm just going to say that right now so we're all on the same page. So for this unit, put a positive sign. If I did the work done by gravity, it's going to be force gravity times where it goes. Force gravity, according to the diagram, is 20 newtons downward, multiplied by the 1 meter to the right. What do you notice about the arrows? They're perpendicular. So what does that suggest? No work. Exactly.
Why is the meters going to the right instead of down?
The reason why is because it's talking about the work done by the object moving to the right with one. Yeah. So that comes from the description, exactly. And quite honestly, that won't change for this whole thing because it's describing this whole situation. Now, if you had different problems, they might change it each time, but this one is always to the right. So I know this is kind of confusing because you're saying 20 times 1 is 0 when it clearly is not. But remember, we're modeling the situation. So the work is 0 because the force and the distance are perpendicular. So this little upside down T is the symbol for perpendicular. So you could write something like that as an abbreviated form. And you could write it exactly like this. You can skip this whole thing if you're like, yep, it's 0. But just give me a quick description like they're perpendicular. So you can actually skip the calculation. For example, if you look at the normal force, it's also going to be perpendicular because normal's up and then the distance is to the right. So you don't even have to do the calculation. You can just simply say, for the work done by the normal, 0 because force normal perpendicular to D. So absolutely take shortcuts, whenever you can. Now, just because the example is not here and I just want to do it, I'm going to add in another force. Force of friction. Let's call it 7 newtons right now. I'm going to throw that in there. Because if we have friction, the work done by friction, friction's going to be going left. The distance is going to be right. What is that going to apply? Yeah, I'll show you. Sorry, I'm just charging my pen. So, what's going to happen is the force of friction is to the right with 7 newtons. I'm sorry, let me start out. So work done by friction would be the force of friction times D. So 7 newtons to the right times, sorry, I'm saying right when it's clearly left. 7 newtons left, 1 meter right. Well, we can still multiply those numbers. 7 times 1 is 7, but we will have negative work for this. Hopefully that makes sense. Friction is going to go against what we're doing. That's what that kind of means here. Negative work. So you get the signs from the direction of the arrows. So if you have all four, like in this case, you could have 2, 0, 1 positive, 1 negative. So that's how you can calculate work here. And all set. What's that? Yes. Yeah, so I when I started learning this, like way back in the day, like I would be like, what work? You know, like especially if you had like a bunch of them, but then like confusing the directions. Like I remember doing that. So the thing that helps me is to draw the direction each time, because then that focuses me on to, okay, is it positive, is it negative, or 0? So I always put the direction in there. That could be more confusing because there's lots going on, but I find that helpful for me at least. So if you are asked to calculate the net work, you need the net force. So if you're given a diagram like the one that I have up here, let's see if you remember. What's the net force of this diagram? Do you remember how to do this? Yeah, 7 newtons to the right. Everyone agree with that?
Yeah.
7 newtons to the right. So if you want to do the net work, you need the net force. So that would be 7 newtons right. For some reason my pen's not charging, so 7 newtons right. Big R for right. I guess I could sort of write it in there. Nope. I'll try again over here. I don't know why my pen didn't charge. 7 newtons right. And then the distance moving right, 1 meter. Work net equals positive 7 joules. That's because both of the directions are right. So it's just an added step. It's not hard in terms of like what you need to do, assuming you remember how to do this, but I assume most of you do. You're just doing it with the net force like this. So I'm pretty sure on your homework, I think you have either 3 or 4 of these types of questions on them. So some just like troubleshooting. Sometimes you just go through it fast. You're like, oh yeah, 20 times 1 is 20. That's the answer. So if you get it wrong, look at the direction. That's usually the first case you should look at. Because actually, if you're doing the work done by, for example, the gravitational force, it should be 0. So you should see that as well. Questions on the calculation? Oh, you gotta go. Yeah. Were they supposed to call you, or? No. Take care. Sorry about that. So since the calculations are pretty straightforward, I'm not going to do another one unless you feel like you need one. Do you feel like you need one? No, that's what I thought. But I will ask, too, if the system is gaining or losing energy, so use the sign of work. If it's positive, you gain energy. If it's negative, you lose energy. And if it's 0, it stays the same energy. So just note on that. Just another quick note, too, is they might ask you the work done by lifting up, like literally like if you're working out and you take an object and you're like lifting it, whether it's like a curl or a push-up or a chin-up. What you're lifting against is gravity. So if they ask you to find the work done by lifting, you need the force of gravity. So they could either give you the force of gravity, easy case scenario, and then you'd find work by force times distance. But in the cases that they don't give you gravitation, they give you mass. You must make it into a force. The way you do that is you add in multiplying by 9.81. Okay. So, a quick example right here. Sarah lifts her body up while doing a pull-up. Calculate the work that she does. So if I were to do her work, notice that they gave us mass, not force. So that means we would have to multiply her mass first by 9.81 to get a force. And then it would be force times distance. So it would look like this. So mass be the force, which would be m times g, and then times d. So it would be 62 kilograms times 9.81. The force is up, the distance is also up, so 0.5 meters. So when you calculate that out, you get 304.11. Of positive work. Like that. So that's just a it's just a quick added step. Another way you could check your work too when you're doing your online homework, if you're finding it's not coming out, try 9.81 or identify that that's mass. Okay, questions on that? All right. And that is it for work. I'm now just going to open up power, and I really just have 5 minutes to talk about power, and then I'll be done for today, and you can work on your homework or whatever you'd like at this point. Power is an extension of work, really. I have way more slides than I need for this. But work and power are related because power is how much work you exert over time. It's kind of like how much energy you put out during a specific time. So I'm just going to write that down too. And a conceptual is how much energy you exert per time. And I'm kind of making work and energy equal each other synonymously. Although really it's a chain of energy, but that's okay. Work and energy are kind of related. So to measure to measure work, to measure power, try again. When we measure power, it's in the unit of watts, and it's joules per second, because it's energy per second. So HP represents horsepower. So back when the study of energy was being done, it was about the time of horse and carriages. So they would say, for example, how much energy does this exert? And they would say, oh, about 4 horsepower, which meant a lot. The actual quantity of horsepower is 746 watts. So you've ever heard cars being described with horsepower before, like 500 horsepower or something like that? They use that to describe how much energy you exert over time. I think you might have a homework question referring to HP, so I just want to mention that HP means horsepower. And the value is slightly different just depending on the context. I have it here, but if the homework is slightly different, use the homework value if that's the case. Quick note about power. So power, anyone recognize this with light bulbs? 60-watt light bulb? Or like a 100-watt light bulb? What this physically means is there's exerting 60 joules per second of energy. For this one's 100 joules of second per energy. Based on that, which one do you think is brighter, 60 or 100? 100. Fun fact, I did not know that when I was first my first apartment, and I had to buy light bulbs. You know, actually, I was in college, and I had my first apartment, and I had lamps and stuff like that, and then I had to buy light bulbs. So I go to Walmart, and there's a shelf full of light bulbs, all different wattages. I was like, I don't know what this means or why I should care, you know. So there was like 40, 60, 75, 100. I went, okay, 60 sounds right in the middle. I chose 60. But actually, what it means is your brightness. So, for example, you might want a 40-watt light bulb next to your bed because it's not super bright and in your face versus like you might want a 100-watt light bulb in the kitchen where you want lots of bright light, or in the basement. So, of course, this is all personal preference, but I didn't realize that that was a thing. So hopefully this story will help you in your decision-making processes when you have to do such a thing, of buying a light bulb, for example, or a hair dryer. Sometimes they put the wattage on hair dryers. That means that that is 800 joules of energy per second. So if you want to dry your hair faster, you need something with higher wattage or higher energy per time. So and we did it in the other class. We're actually going to talk a lot more about this when we do electricity, but we actually calculate the cost of this, and we found out it costs like this is probably wrong, but I'm going to say it like 9 cents every time you blow dry your hair, and I know that doesn't sound like a lot of money, but think about all the other things that are plugged into your house, right? Like that adds up very quickly. So it's pretty interesting. We're going to do a whole study on this. But anyway, really quickly, I think this calculation is also very straightforward. It's just the energy divided by time. But keep the time has to be in seconds once again. So another very important note is that if you have it in hours and minutes and all that fun stuff, it has to be converted to seconds. So I'm going to do one quick example and then we'll be all set. Hercules. He exerts 100 joules of energy per 10 seconds. What's his power? Well, all of you know or can guess that we're going to calculate his power by taking the total work and dividing by the total time. Since it's in seconds, we don't need to do anything, so 100 divided by 10 gives us a beautiful, easy number of 10 watts. Fun fact, watts looks like work. The symbol for watts and the symbol for work are the same. So you need context. So for power, it's 10 watts. For work, F times T. D like this. So just be careful with that. I just know that's super confusing. They are the same symbol. Ways you can double his power. You could double the force, because that would double this, or you could have the time. That would give 20 watts instead, doubling your power, right? If I did 100 divided by 5, I would get 20. And if I did 200 divided by 10, I would get 20. That's how you could double the power. So something more powerful exerts a lot more energy quicker. It's another way to say that. So I could make this a little harder by making you calculate the work first. In this case right here, force and distance. I'm just going to show you super quick, although I think all of you will see that you're actually not given work, you're giving a force and a distance. So power would be, work would be 2 numbers on top, and then the 10 on the bottom. So 400 over 10 gives you 40 watts. So if you're not given work right away, you should be able to find work. I won't make it super out of your reach, but if you're not given work, you have to find work first and then do the calculation. I did that right? 200 times 2, 400, yeah. Just double checking. We are on video here. Okay, any questions? Okay, that concludes our video on work and power. These are just examples that you can do, including the lifting example, showing you different ways to show that. And this is just information about power. You can have it, express it in watts and kilowatts, for example, for bigger values. And then a typical multiple choice question, which one's more powerful, so we'd have to calculate each of these. And that's what you have here. If we have time, we'll do the power challenge, where you can see how fast someone can run up a flight of stairs and see who's more powerful at doing that. So a little later, if we have more of a classroom and time, I'll show you how we can do this. Yeah. All right, that's it.